Hello everyone. The Moon, our closest celestial neighbor and Earth's only natural satellite, has fascinated humanity for centuries. Understanding how the Moon formed has been a long-standing question for scientists, leading to the development of various theories. These theories, which examine the Moon's chemical composition and physical characteristics, aim to explain its relationship with Earth. The most widely accepted theory is the giant impact hypothesis, alongside alternative ideas such as the co-formation, capture, and fission theories. Comprehending the Moon's formation provides valuable insights not only into the Moon itself, but also into the early history of Earth and our solar system. Scientific research, space missions, and technological advancements have given us the tools to delve deeper into the Moon's mysteries. Additionally, the Moon holds significant cultural and historical importance, influencing everything from mythology to calendar systems. The Moon's diameter is about 3,474 kilometers, which is roughly a quarter of Earth's diameter. To put it in perspective, if Earth were the size of a basketball, the Moon would be the size of a tennis ball. The Moon's surface area is around 37.9 million square kilometers, comparable to the surface area of the continent of Africa. On average, the Moon is about 384 to 400 kilometers away from Earth. That's like traveling around the Earth's equator almost 10 times. This distance varies because of the Moon's elliptical orbit. At its closest approach, perigee, it's about 356,500 kilometers away, and at its farthest apogee, it's about 406,700 kilometers away. The Moon's surface is dotted with craters of all sizes, formed by the impact of asteroids and comets over billions of years. One of the largest craters is the South Pole Aitken Basin, which is about 2,500 kilometers in diameter and 13 kilometers deep. Imagine a crater so big it could fit the entire United States. These are large dark plains on the Moon's surface, created by ancient volcanic eruptions. Despite being called seas, they contain no water. One of the most notable maria is Mare Imbrium, the Sea of Rains, which is about 100 kilometers in diameter. These vast, flat areas make up about 16% of the Moon's surface. The Moon also has impressive mountain ranges and deep valleys. The Apennine Mountains, for instance, stretch about 600 kilometers. The surface features also include rills, which are long, narrow depressions or valleys that can be up to 4 kilometers deep. The Moon's crust averages about 50 kilometers in thickness, but can reach up to 100 kilometers in some areas. It's made mostly of silicate minerals, specifically a type called anorthosite, which gives the highlands their bright appearance. Beneath the crust lies the mantle, composed of magnesium and iron-rich silicate minerals. Ancient volcanic activity brought basaltic rocks from the mantle to the surface, forming the maria. The Moon's core is relatively small, with a radius of about 350 kilometers, and it's partially molten. It's rich in iron, but significantly smaller compared to Earth's core. These essential features help us understand the Moon's physical structure and characteristics. Its size and distance from Earth, the craters and maria on its surface, and its internal composition all provide clues about how the Moon formed and evolved. Now that we've covered the essential features of the Moon, let's dive into one of the fascinating theories about how the Moon formed. The fission theory suggests that the Moon was once part of the Earth and was flung out into space due to the rapid rotation of the early Earth. This idea was first proposed by George Darwin, son of the famous naturalist Charles Darwin, in the late 19th century. George Darwin hypothesized that the early Earth was spinning so quickly that a part of its mass separated and eventually formed the Moon. One of the key pieces of evidence supporting this theory is the similarity in the chemical composition of the Earth's crust and the Moon. The rocks from the Moon brought back by the Apollo missions show that the isotopic compositions of oxygen are nearly identical to those on Earth. This suggests a common origin. Additionally, The Pacific Ocean basin was once thought to be the site where the moon might have separated from the Earth due to its massive size and shape. However, despite these intriguing clues, the fission theory has significant challenges. For the Earth to spin fast enough to throw off a chunk of itself, it would need to rotate once every 2.5 hours. This is much faster than the Earth has ever been known to rotate. There is no direct geophysical evidence indicating that such a rapid spin and subsequent fission event occurred. Modern computer simulations and models of planetary formation do not support the conditions required for the fission theory. The angular momentum and energy required for such an event do not match the current state of the Earth-Moon system. While the fission theory provides an interesting perspective on the Moon's formation, it has largely been overshadowed by the more widely accepted giant impact hypothesis. This newer theory explains many aspects of the Earth-Moon system more comprehensively, including the similar compositions and the angular momentum. Now let's take a closer look at another fascinating hypothesis. The capture theory proposes that the Moon formed elsewhere in the solar system and was later captured by Earth's gravitational pull. This theory suggests that the Moon was a wandering body, possibly a protoplanet or a large asteroid that came too close to Earth and was captured into orbit. Formation location. According to this theory, the Moon formed independently, possibly in a region of the solar system with different conditions and materials than those of Earth. For the Moon to be captured by Earth's gravity, a significant loss of energy would have been required. This could have been facilitated by a collision or close encounter with another celestial body, which slowed down the Moon enough to be captured by Earth's gravity. One of the initial supports for this theory was the idea that the Moon might have a different composition compared to Earth, suggesting it originated elsewhere. However, lunar samples show that the Moon and Earth have very similar isotopic compositions, particularly in oxygen isotopes, which indicates a common origin. The mechanics of capturing a large body like the Moon into a stable orbit around Earth are highly complex. Simulations show that it would be incredibly difficult for Earth to capture such a large object without an additional body to dissipate the energy. There is a lack of geophysical evidence supporting a capture event. No known large-scale collisions or close encounters could account for the energy loss required for such a capture. While the capture theory is an interesting concept, it faces significant challenges. The theory does not adequately explain how the Moon could lose enough energy to be captured without some form of catastrophic event or third-body interaction. Chemical similarity. The chemical similarities between the Earth and Moon suggest they share a more intertwined history than a simple capture scenario can explain. Due to these issues, the capture theory is less favored among scientists compared to other theories like the giant impact hypothesis, which offers a more comprehensive explanation for the Moon's origin and its relationship with Earth. The co-formation theory suggests that the Moon and Earth formed together from the same primordial accretion disk of gas and dust that surrounded the early Sun. According to this idea, as the solar system was forming, the material that eventually became Earth also formed the Moon in a shared process. Key aspects of the co-formation theory. The theory posits that Earth and the Moon were created at the same time from the same cloud of material, meaning they would have similar compositions and a closely linked origin. This scenario implies that the Moon's formation was a natural consequence of the formation of Earth, occurring in a disk of gas and dust around the young Sun. Evidence and challenges. One of the main pieces of evidence supporting this theory is the chemical similarity between Earth and the Moon, especially in their oxygen isotopes. This similarity suggests that the Moon and Earth share a common origin. The co-formation theory accounts for the Moon's relatively close orbit to Earth and its synchronous rotation, which means it always shows the same face to Earth. While Earth and the Moon have similar isotopic compositions, The Moon's surface is composed largely of basalt, which differs from the Earth's continental crust. This discrepancy suggests different formation processes. Current models of planetary formation show that forming a large moon from the same material as Earth would require specific conditions that are difficult to reconcile with the observed properties of the Earth-Moon system. Despite these challenges, the co-formation theory remains an important part of the discussion about the Moon's origins. It provides a plausible explanation for some of the similarities between Earth and the Moon, but is less favored compared to the giant impact hypothesis, which better accounts for the differences observed. The giant impact hypothesis suggests that the Moon was formed from the debris resulting from a colossal collision between the early Earth and a Mars-sized body named Theia. This theory proposes that about 4.5 billion years ago, during the early formation of the solar system, Theia struck the young Earth in a cataclysmic impact. Key aspects of the giant impact hypothesis. The impact would have released an immense amount of energy, causing a significant portion of the Earth's outer layers and Theia's material to be ejected into orbit around Earth. This ejected material eventually coalesced and formed the Moon. The debris formed a ring around Earth that gradually came together due to gravitational forces. Evidence supporting the giant impact. Hypothesis. One of the strongest pieces of evidence is the similarity in the isotopic composition of Earth and Moon rocks, particularly oxygen isotopes. This suggests that both bodies originated from the same source. Angular momentum. The current Earth-Moon system's angular momentum aligns well with the expectations from giant impact simulations, which show that such a collision could create a moon with the observed orbital characteristics. Lunar composition. The Moon's composition, especially its lack of a significant iron core, supports the idea that it was formed from material that was primarily from the outer layers of the Earth and Theia. While the giant impact hypothesis is widely accepted, ongoing research and simulations are refining the details of the impact event, including the exact size of Theia and the nature of the collision. Alternative models. Researchers continue to explore variations and refinements of the giant impact hypothesis to address details and discrepancies in the formation process. Despite some ongoing debates and refinements, the giant impact hypothesis remains the leading theory for explaining the Moon's formation. It provides a comprehensive framework that explains the similarities and differences between Earth and the Moon and aligns with current observations and simulations. And that wraps up our exploration of the Moon's formation theories. From the co-formation theory to the giant impact hypothesis, we've covered a range of fascinating ideas about how our Moon came to be. Each theory offers a unique perspective and has contributed to our understanding of the Earth-Moon system. The giant impact hypothesis, with its compelling evidence and alignment with current observations, remains the most widely accepted explanation. However, science is always evolving, and ongoing research continues to refine our understanding of this cosmic event. If you enjoyed this deep dive into lunar science, don't forget to give this video a thumbs up, subscribe to the channel, and click the bell icon to stay updated with our latest content. We've got plenty more intriguing space topics and scientific discoveries coming your way,